Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from the Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on the module Photometric Techniques and Photometric Types under the paper of Astronomy and Astrophysics. After completing this module, the students will be able to learn a few basic processes which show how photometry as an observational tool in astronomy helps in establishing some of the important characteristics regarding the variable stars. Number 2, know that there are different types of photometric device with each having its own unique application of observational value. Number 3, to learn the concept involved in the working of some important photometric device. To know that the photometric techniques such as differential photometry lead to the conclusion that variable star formation in the universe is a general phenomena and all the variable stars undergo luminosity variation, and the nature of different types of variable stars is best understood by latest photometric techniques. Starlight, as we know, comes to us from astronomically large distances and enters the Earth's atmosphere before being captured by our telescope for further analysis. In its crude form, the atmospheric disturbances introduce technical difficulties in the proper analysis of its spectra received. It's therefore recommended to try to find the best way for observing the pure spectrum of the stars. When we talk about the variable stars, so these variable stars can only be distinguished by perceptible change in the luminosity output. The atmospheric disturbances obscure the results and the analysis is seriously affected. Our task is to remove the signature of the atmosphere and instrument and try to recover as much information as possible from what entered the Earth's atmosphere. We talk here about the photometry of variable stars. Variable stars can be distinguished by the amount of light received from them. The intensities of light received from the two sources constituting a pair of variable stars follows inverse square law. Let's suppose that E denotes the intensity of the illumination of a surface due to a light source and R be the distance between the source and the surface. Assuming L to be the luminous intensity or illuminating power of the source, then the relation between the energy E and the L is defined by E is proportional to L. Also, we have said that the energy of these variable stars, it follows the inverse square law, so that is E is proportional to L by R square. By combining these two equations, we will have E proportional to L by R square, or we can write E is equivalent to K times L by R square, where K is a constant of proportionality and is defined by k is equal to 1 by 4 pi. The factor 4 pi is introduced due to spherical nature of light source. Therefore, we write E is equivalent to L by 4 pi r square. So, utilizing the principle of photometry for a pair of variable stars having the intensities of illumination as E1 and E2 with their corresponding distances defined by R1 and R2 from the point of observation, then we can simply say that the following relations are valid. Number 1, E1 is proportional to L1 by R1 and E2 is proportional to L2 by R2, where, as already said, that L1 and L2 are the luminous intensities of the two sources. So, by adjusting the distances denoted by R1 and R2, E1 and E2 can be made to be equal. That is, E1 is equal to E2, and we can write L1 by R1 is equal to L2 by R2. The relation that L1 by R1 is equal to L2 by R2 suggests that if the luminous intensity of one source is known, by comparison, one can determine the luminous intensity of the another source. An instrument for comparing the luminous intensities of two variable sources is known as a photometer. One of the most accurate photometers used for comparing the luminous intensities of two sources is Lumer-Brodom photometer, as can be shown in this given two diagrams. So we have the block diagram of Lumer-Brodom photometer. Here we can see we have the two sources here, and the entire sketch-up of this is the block diagram. The other one is basically a laboratory type of this Lumer-Brodom photometer. So we will have different types of photometric devices. Depending upon the experimental requirement, different photometric devices are used to compare the intensities of a given source. Almost all photometers measure relative rather than absolute intensity. Some of the popular photometers that have been used in photometry of variable stars are like here as. So we have the Bunsen, we have the Rumford, we have the Lumer-Brodom, we have the handheld, we have the benchtop and luminance. So things can be done for all these photometers to look for their working principle and to look for their intensity comparison and to look for their current comparison and so on. The high definition photographs of laboratory type current based photometers are also shown here. So this is what we can call it as a handheld photometer. One of a very important feature of this handheld photometer is that it can be easily taken in the hand and used anywhere in the laboratory. We have one more sketch here that shows the benchtop photometer. We have here one more sketch here that shows the luminous photometer. Some important photometric results. Telescopes have range 0.6 to 1 meter and equipped with photometers using photomultiplier tubes and are used to achieve very good observational results. The transparency variations need to be determined drifting apart of the channels. This can introduce severe errors. The present limit to the photometric precision is still just slightly under 1 millimagnitude. With good photometric photometers under excellent weather conditions. So therefore, these weather conditions have an important role here. In fact, considerable observational care has been is to take has to be taken in reducing the observational errors sufficiently in order to obtain the old limit near 1 millimagnitude precision per single measurement. So we discuss here one of an important figure that represents the light curve of the variable star FG and two comparisons taken with the 3-star technique. In the given figure, we have a solid curve and the dots. The solid line has been calculated to be fit for 24 frequencies detected after the 1995 FG Global Observer Companion. If you see the variation of this luminosity, that is the brightness with time. In this given figure, the time period is plotted along the x-axis and the luminosity means corresponding to its brightness is plotted along the y-axis. So we have the 4 parts that have been plotted here. We have the red dots, they denote the FG and then we have the plus, that is the comparison 1. We have the cross, that is the comparison 2, and we have the solid line that denotes the best fit. 3-star photometry. So this is a kind of a photometry used here. We call it a 3-star photometry is another observing technique for understanding the true nature of the variable stars. In this technique, intensities of two given stars under the appropriate sky background are measured successively with the same photomultiplier tube. So, like C1, C2, sky and so on. In case of a large sky brightness gradient, so moon or dusk or dawn, the intensity has to be measured for each star separately. An integration time of 40 seconds per star has turned out to be a good compromise between high precision and short cycle time. In this case, the cycle time is about 6 minutes. The advantage of this observing technique, so which we have called it as a 3-star technique, lies in its long-term stability. The sensitivity drift of the photometer and the transparency variations of the atmosphere can be corrected for. Pulsation periods of few hours can be determined with high precision. For shorter periods, another observing technique called as charge coupled device photometry, generally referred as CCD photometry, has to be applied. CCDs are sensors used in digital camera and video cameras to record still and moving images. They capture light and convert it to digital data that is recorded for future use. Hence, CCD is often considered the digital version of the film. The presence of many comparison stars are on the same frame and the ability to observe through non-photometric, so-called spectroscopic weather conditions make CCD detectors invaluable. To achieve millimagnitude precision, a good guiding system is needed. Bias frames and flat fields, about 10 to 20, have to be taken each night before and after the run, and linearity checks have to be performed accordingly. While doing this observational photometry of variable stars, there is a need to look for the differential photometry. For differential photometry, we look for the theory of this differential photometry. In the theory, we start our observation of variable stars in the open sky by estimating the difference in magnitude between a given pair of variable stars that in turn depends upon the color difference and their respective air masses. So this is called Boger's law. In the case of beta and V measurements taken at two different air masses xj and x1 and x2, the following relation can be written. Delta V is equal to delta V minus k prime V into delta x plus del dot of delta of B minus V. So delta of B minus V is equivalent to beta times delta of small b minus small v minus beta into k prime bv delta x minus beta dot k prime bv delta of b minus v and the average of x. So we can write, we will have here a delta x. So delta x will correspond to x1 minus x2 and average of x will be given by x1 plus x2 divided by 2. Lowercase denotes color difference and the air masses. Instrumental magnitudes at a given air mass, while uppercase denote extra atmospheric values in the standard system. The above equations that we have just described have been derived by taking into consideration the basic equations of the atmospheric physics, which is defined by I is equivalent to I naught exponential of minus k dot h, where I naught is the intensity outside the atmosphere and I is the value measured after traversing a thickness h, and k, the letter capital K, is the absorption coefficient per unit length characterizing the properties of the absorbing medium. K dot h is called actually the optical depth. So after taking logarithms, we can rewrite this in magnitudes as small m is equivalent to m naught minus k dot h, where x is the air mass and small k is called the extinction coefficient per unit air mass. Following two very important graphs here and their results from the Lashila Observatory in chill type, the relation between the extinction coefficient and the corresponding wavelength for different air masses at the plate. So coming to this figure, we have the wavelength in nanometers to be plotted along the x-axis and the extinction coefficient to be plotted along the y-axis. So we have different measurements in this very plot. And then the other plot, we have also variation of average extinction coefficient corresponding to the wavelength. Atmospheric, also in this graph, we have different parameters that have been plotted in this graph. The atmospheric extinction coefficients depend on wavelength and on the altitude of the observing site. They can vary with time, from season to season, from night to night, and within a single night. So let us discuss the extinction coefficient and its interpretation. For the measurement of the extinction coefficients in the case of variable stars, we have to take into account a dependence on their respective color magnitudes. For a broadband filter having a central wavelength lambda and an associated color index C0, we have the relation k lambda is equal to k lambda dash minus k into delta lambda into C0. So this relation seems to be important in the sense that we can talk about the various interpretations of this extinction coefficient. The first order term in equation 17 is the proper atmospheric extinction, while the second order term takes into account the dependence on object color due to the width of the filter band pass. The first term varies with time, but the second term usually remains constant for a given instrumental setup. To determine the extinction coefficients accurately, we observe a set of standard stars spanning a wide range of colors for several values of the air mass, but before and after meridian passage. A faster, separate determination of the primary and secondary extinction coefficients is possible by observing pair of stars having the same known color at low and high air mass. So ascending or as well as descending to the second order term so that the second order term vanishes. For pairs of stars of having different known color and located in the same field of view at different air masses, the first order term can be neglected. If extinction is unknown, we measure pairs of stars under a given program and the standard stars at the same air mass. For unknown and variable extinction, the standard stars are picked up as close as possible in the sky to the program stars. A range of extinctions obtained alternatively helps in interpolating any extinction changes that may take place during the course of the extinction measurements. So students, let us see what we are going to learn in this module. The main aim of this module has been to understand some of the basic photometric techniques for carrying out the necessary observations regarding the existence of variable stars in the visible universe. We have attempted to critically analyze some of the important photometric results received from variable sources. The spectral characteristics of variable stars have been given proper treatment by introducing the theory of differential photometry and by evaluating some important parameters such as extinction parameter. Thank you.